Humans are pretty coordinated, almost impossibly coordinated. Some humans are able to hit a ball that's traveling at over 150 kilometers an hour. How can they do that? I mean, if you didn't really think about this for a second, it seems impossible. There are delays in the time that it takes for the neurons in your brain to process new information that's coming into your senses. And the amount of delay is actually about 100 milliseconds, which is kind of an eternity. In the context of this ball flying from a baseball pitcher to a baseball batter, 100 milliseconds is 5 meters. And if you're using information that's 5 meters off in trying to hit this little ball, there's no way you're ever going to do it. So somehow the brain is able to overcome this delay in the neural signals that allow us to perceive information. And we still manage to hit the ball. How can we do it? Another challenge is the idea of desynchronization. We don't actually perceive everything about that ball at the exact same moment. Yeah, there's about a 100 millisecond delay, but that 100 millisecond delay is different depending on what aspect of the ball we're talking about. So to convince yourself of this, take a look at these quickly flashed arrays of letters and try and detect which of the flashed arrays have any red letters intermixed amongst the white letters. And it's pretty easy. Whenever there's a red one, it just pops out and you know immediately. Now, by contrast, let's take a look at these displays, and these are actually the same displays, and now try and tell me which of these displays have O's in them in addition to the C's. Not so easy. In fact, at the rate that I'm showing it to you, it's just about impossible, unless you happen to get lucky and have your eyes resting at exactly the location that there happens to be a C popping up in the sea of O's. So what we can see from this example is that color information is detected very quickly, but form information is a bit slower. And it turns out that motion information is somewhere in the middle. So if we think about that baseball hurtling at the batter, so they're not going to perceive a baseball hurtling at them. Instead, they're going to perceive something along the lines of beige, fast, circle. And that, again, is going to make it even harder to hit the ball. Do you swing at the beige? Do you swing at the fast? Do you swing at the circle? Well, how are you supposed to do this? So these challenges of neural delays and desynchronization led Hinze Hogendoorn of the University of Melbourne to propose a new model for the way that humans perceive the present moment. And basically, the idea that he's putting forward is that we don't actually perceive a present moment. We predict the present based on our very recent past. And the brain's representation of this is actually an extended moment that extends a little bit into the future as well as a little bit into the past, straddling the present. And this has a lot of implications when we think about how humans are trying to develop AI, and in particular, how we're trying to develop autonomous cars. I think the intuition that a lot of us walk around with for the way that we perceive the present moment is that information comes into our retinas and our other sensory organs, and it just gets projected immediately into our brains in such a way that we're able to experience the moment in a very immediate and real way. But it turns out that that's not true. We don't actually experience the present moment ever at all. We live entirely in a projection of a predicted present that our brains are making up all the time. So if we think about how we're developing AI and how we're trying to make autonomous vehicles, is this a challenge that the programmers of autonomous vehicles are going to have to struggle with? And, for about 10 years now, we've heard that autonomous driving is only about 5 years away. But we've heard that for about 10 years. So maybe part of the challenge is that the programmers, and I'm no expert on autonomous driving, but maybe part of the challenge is that the programmers trying to come up with autonomous driving algorithms haven't properly considered how to perceive the present. Hi there, my name's Adam Dede, and welcome to a Neuroscience Journal Club, where I bring you a weekly discussion of a recently published peer-reviewed article from the world of neuroscience. Perception of the present moment is the core of our conscious experience, and intuitively we believe that this happens in an immediate and real way, such that we are in direct contact with the world exterior to our skulls. And this is represented in this figure. So the gray and black boxes are the frames of an old-time movie reel, and they symbolize the passing moments of time in the world. The x-axis here represents the passage of time, and as you can see, our sensory organs, which are physical objects in the world, are situated at the present moment. And the senses are sampling a slice of information from the stream of events in the world, and this is represented by the white box through the movie reel. Our intuition is that the brain represents a slice of time that is the same as the slice of time being sampled by our senses. In other words, we live in a constant present that is a faithful representation of the objective present happening right now in the exterior environment. The problem is, as we talked about in the beginning of this video, there are neural delays. We don't actually perceive information in the same second or instant that it hits our sensory organs. And if you want to convince yourself of this, get a friend and get a ruler. Have the friend hold the ruler such that the tip of the ruler is sitting between your thumb and index finger. Then, without warning, have your friend drop the ruler. Your task is to try and stop the ruler from hitting the ground by grabbing it as it falls between your fingers. What you're going to see is that you'd never manage to grab the ruler at precisely the tip. Always the ruler will drop some distance before you manage to grab it. And that distance that it drops is an indication of how much lag there is in your perceptual processing. So now, if we think about this idea of neural delays and we go back to this movie reel idea of perception, this is going to lead to an idea that actually the slice of reality that our brain is representing is always being drawn from some distance in the past. And okay, fine. But how do we hit baseballs then? How do we drive cars? How do we do anything where a 100 millisecond delay becomes catastrophic, which it turns out is actually quite a lot of things? The problem gets worse though, because remember we talked about desynchronization, and you saw that color and form and a host of other aspects of the visual world are actually coming into your perception at different times. How do we deal with that? Because now if we think about this desynchronization idea with respect to the movie reel idea of perception, you can see that actually not only are we always representing a bit of information from our recent past rather than the actual present, we're actually representing information from a range of different pasts rather than any specific time in the past. This creates ambiguity about when in time any event actually happens relative to any other event. How do we get around that? Which would obviously become even more catastrophic when we think about actually behaving in the real world, where events do happen at particular times. And then lastly, the problem not only gets tough, it gets weird. Because we always assume, and in both of these examples of neural delays and desynchronization this holds true, we always assume that only things in the past can ever affect things in the present or the future. You can't have something happen in the future that causes a change in the past, right? There's no such thing as backwards causality. Well, it turns out in the land of the brain, actually, you can. So to convince yourself of this, keep your eyes focused on the white cross. You're going to see a green circle jumping from the left to the right. And as you may have guessed, the screen is only ever presenting a static green circle. But still, you'll notice that your brain perceives the impression of motion from one position to the next. It tries to fill in the gap with an approximation of what it thinks has happened. What's crazy about this is that because the jump between the left and right position is random with respect to the vertical direction, your brain has no way to predict where the circle is going. The impression of motion that it's giving can only be filled in after the second circle is presented. In other words, the impression of motion uses information from the future. So now, thinking again about the film reel of world time, what this implies is that the brain's representation is not only delayed, not only desynchronized from multiple points of time, it also somehow draws on information from the future. How can this possibly be? So Hogendoorn proposes that these inconsistencies can actually be reconciled if we change a little bit what we think of as the brain's perception of the present moment. And a simple starting point is to ask, what does that even mean? Present moment. How long is a moment? Hogendoorn suggests that actually the present moment is no moment at all, but actually a very short period of time that lasts several hundred milliseconds. And this figure gives you the general idea. So now the movie reel of objective reality is composed of several different aspects of vision. Each frame within each visual modality represents a moment of time. The thick black line represents the present moment in world time. The entire span of perceptions shown here is the present moment as represented in the brain. The broken dashed line is the sensory horizon. This is the line between time points that the brain has fully processed and time points that the brain is forced to make predictions about. As you can see, the objective present is firmly in the predicted portion of the present moment. You can also see that the sensory horizon is different for different aspects of perception. For example, color is ahead of motion. So thinking about this, what does it mean for that jumping circle that we just looked at a few seconds ago? So let's ignore the problem of desynchronization and just focus on a unified representation of the green circle on the computer screen. Let's say the series of frames on the top row represents the brain's perception, and the series of frames in the bottom represents the objective world. The dashed white line represents the sensory horizon, and the solid orange line represents the objective present moment. As you can see, for times 0 through 3, the brain has done a good job, accurately representing the world. This is despite the fact that neural delays mean the brain has only received information about times 0 and 1 so far. It just makes the unremarkable prediction that nothing changed in times 0 and 1, so it's unlikely to see changes in times 2 or 3 either. So let's move forward in time. As you can see, at time 4, the circle disappears. But because of neural delays, the information hasn't reached perception, so the old prediction of a still circle persists. At time 5, the circle reappears at its new location down in the bottom right, but the brain still hasn't even registered its disappearance, and the mental representation is still showing the ball in the top left. It takes until time 6 for the brain to perceive that the circle disappeared in time 4, but it doesn't necessarily update its perceptual representation. There could just be noise in the sensory input. Finally, at time 7, the brain registers sensory information from time 5 and knows that the circle is now in the bottom right. That is incontrovertible proof that the brain's representation of time 5, 6, and 7 were wrong, so these are discarded as errors. What's more, because the brain knows that objects in the world cannot teleport, it revises the entire timeline under the assumption that there must have been a rapid continuous movement which was missed during the processing of earlier sensory information. After all, our brains did not evolve with computers, and in the real world, any object jumping from point A to point B must have traversed the intervening points. So what this example shows us is that the brain is constantly making predictions, and those predictions can sometimes be wrong, and when they are wrong, the brain simply corrects them with its best guess. One interesting thing, though, is that we don't seem to notice any of these errors. We're entirely amnesic for the fact that our brain is constantly making predictions that constantly end up being wrong, or at least a little bit. And we know that they must be wrong because any prediction is going to be error-prone. There's going to be situations where we don't manage to predict things perfectly. But yet we manage to hit fastballs, so we know that the brain is indeed making predictions. Simply put, the brain is hiding these errors from us. So now, going back to Hogendoorn's title for the paper we're talking about today, I think we can start to understand what he's trying to get at. Perception in real time, predicting the present and reconstructing the past. A key prediction of this model, then, is that there should be brief periods of time where the brain predicts certain events in the present moment, which then do not come to fruition. And these incorrect predictions should be represented in neural activity, even if that neural activity is quickly rewritten when new information comes in. And in a recent experiment carried out in Hogendoorn's lab by Tessel Bloom, it was found that indeed there was some evidence to suggest that there are these kind of prediction-driven yet erroneous brief representations in the brain. So specifically, what Bloom and her colleagues were looking at was EEG signals taken from the brain while participants were viewing a series of wedge-shaped objects that were being presented on the computer screen. So to get a sense of what this looked like, you can see this series of wedges being presented, and you can see that pretty quickly you get an easy sense of where the next one will be presented. But then suddenly, if there's a reversal, like that one right there, you can see that your prediction is going to be wrong, at least for a brief period of time, and it's going to take you a little bit of a second to realize, oh, oops, the motion has switched directions, and now I have to alter my predictions. So the question that Bloom and Hogendoorn wanted to look at was whether or not there would be evidence in the neural activity that would tell them about the brain's incorrect predictions. Indeed, what they found was that the brain's representation of unpredictable stimuli was about 17 milliseconds slower than their representation of predictable stimuli. So what this tells us then is that there's some kind of lag or conflict that has to be overcome when the brain is trying to represent information that couldn't have been predicted. This certainly indicates that unpredictable stimuli are harder to process than predictable stimuli, but I don't think anyone would have questioned that. The real thing that Hogendoorn's theory predicts is that early in processing, there should have been a neural representation of a predicted but incorrect stimulus, and then later in processing, a representation should have developed of the actually correct stimulus. So if we imagine an analysis taken at different points in time relative to stimulus onset, at the initial onset of the stimulus, we should have seen that the brain's decoded position was actually entirely incorrect, representing its initial prediction. But then, over time, evidence for that predicted but wrong position should have dropped down to 0, as evidence for the unpredicted but it turns out correct position would have risen over time. That's not exactly the analysis that Hogendoorn did, but I think that there could be a lot of technical reasons why that analysis wasn't necessarily feasible with the data set that they had. All in all, though, I think that Hogendoorn's theory goes a long way to giving us a good conceptual understanding of how it is that we perceive the present moment. And in actual fact, we never do. We only predict it. And our present moment isn't even a moment. It's a spread out smear across time that lasts several hundred milliseconds. We only fail to detect this because we don't lay down memories of the changes that occur in this several hundred millisecond period of trying to make a best guess. We only put memories down for the things that pass out of the present moment and into the past, by which point we've stopped editing. I think what's going to be really interesting to see is whether or not we're able to come up with artificially intelligent systems that can get around this issue of neural delays, desynchronization, and seeming causality violations. Will it be possible to have an automatic driver that does not have to rely on predicting its present, but can actually know it's present in some kind of a veridical way? I tend to think it's not going to be possible, because even if we get the lags on all of the electronics in a self-driving car down to as close to 0 as possible, there's always going to be some lag. There's always going to be some processing time. And I don't really think that's something that we're going to be able to bring down to 0. So at the end of the day, if we really want to be able to create self-driving vehicles, we're going to have to create future-telling machines first. Anyway, that's it for this time. If you liked the video, please like, subscribe. If you have any comments, questions, concerns, please jump down to the comment sections. I'd love to hear your opinions on this topic. All right, thanks. Catch you next time.